Hello, calculus fans. In this section, we are going to use a technique called partial fraction decomposition to help with integrating rational functions. So we're going to learn how to integrate any rational expression. A rational expression is just a ratio of two polynomials. So remember, a polynomial is just an expression with non-negative integer exponents. So, the things we see, 3x to the fourth minus 5x squared plus 7, polynomial. As long as the powers are non-negative integers, you're okay. So you can have things like x to the 7th, minus pi x to the 4th plus the square root of 2. You can have numbers that are any real number, just the powers have to be non-negative integer exponents. So those are polynomials there, but something like 5x to the negative 2 is not a polynomial because that's a negative exponent. Or something like the square root of x or 1 over x, because this is x to the 1/2 power and this is x to the negative 1 power, okay? But a rational expression is just a ratio of two polynomials, one polynomial over another polynomial, like this. This is a rational expression right here, polynomial divided by a polynomial. So to get started, let's consider this expression right here. And I just want to go through and expand this and see what happens. But first I want to just review kind of an easy way to add or subtract fractions. So if you have something like 2/3 minus 1/5, the way we were all taught this in elementary school is, okay, get a common denominator, and then you change this subtraction problem into a new subtraction problem where you have a common denominator, and these problems would be equivalent, but then you can actually do the subtraction and get your answer. And it's fine. That's the way it should be taught. But then there's also a shortcut. And let's just do the shortcut here because the shortcut we use here can be used on rational expressions too. So the shortcut is you just multiply the two denominators together because that will for sure give you a common denominator. Might not be the least common, but you can always simplify later, but it would definitely be common. So I'm just going to multiply these together. 3 times 5 is 15. And then the process of getting a common denominator and going through all that stuff that we learned can be simplified just by multiplying here. 5 times 2 is 10. 3 times 1 is 3. And then you just go 10 minus 3 to get 7. Okay, so that's kind of the shortcut way to do it. But that shortcut works on these too. So I don't have to actually multiply this by x plus 2 over x plus 2. And I don't have to multiply this by x minus 3 over x minus 3 to get a common denominator and go through all that. I can just do the shortcut method. So I'm just going to multiply the two denominators together. And then I'm going to multiply crossways this way. So I'm going to get 3 times x minus 3, which I'll write over here. So 3 times x minus 3, and then minus 5 times x plus 2. Okay, and then what we would do is just distribute the 3, distribute the negative 5. And when we do that, we will get 3x minus 9 minus 5x minus 10 all over x plus 2 times x minus 3. And then this cleans up to minus 2x minus 19. And then if I were to expand the denominator by just multiplying, like FOIL method, right, then I would get x squared. And I'm going to get minus 3x plus 2x, which is minus x. And then last times last gives us minus 6. Okay, so we started here and just did some, basic arithmetic and ended up over here. Okay, and that's fine. So like if we wanted to integrate this expression, which is this one right here, what we can do is just rewrite it as this, and then it's easy to integrate because you can see this is definitely not a known integral right here. But if we rewrite it this way, then it's kind of easy. So the task for today is to start here and get back over here. It's much easier going in this direction, but there is a technique we can use that isn't too bad to go in this direction. Because now we could actually solve this example too. If we have an integral like this, we could just rewrite this integral as 3 over x plus 2 minus 5 over x minus 3 dx, right? And we know with integrals like this, we can split this up into two integrals. So we could say this is equal to 3 over x plus 2 dx minus 5, minus 5 over x minus 3 dx. And then what I'm going to do is just going to pull these constants out front. Okay, so I'm going to write this as 3 times 1 over x plus 2 dx minus 5 times 1 over x minus 3 dx. And now we've got pretty easy integrals here. So this one, you might be able to see the solution just by looking at it, but you probably will after I do this one. So I'm going to do that one off to the side here. So let's say we are in a calculus class. We just learned about u substitution. So from this one, we could do u substitution. We could say, well, let's say I'm going to let u equal x plus 2. Then du will just be 1 dx, right? So I could substitute this in and get 1 over u du. That's going to be the natural log of the absolute value of u plus c. And so it's natural log of the absolute value of x plus 2 plus c. So when the lead coefficient in front of this x is a 1, it's really easy. We can pretty much go right to the answer. So over here we've got 3 times the natural log x plus 2. And then look at this one. This is going to be very similar, right? So if this is this answer, then this one is just going to be minus 5 times natural log of the absolute value of x minus 3 and then plus c. So the only thing that could go wrong here is if, well, not wrong, but if there were a 2 here, let's say this is 2x plus 2, and you have a 2 here, so u equals 2x plus 2, so then du would be 2 dx, so then we have to go 1/2 du equals dx. So then we have like a 1/2 out in front of this, right? So that's the only thing to be careful about. But if it's just a linear denominator like this with a lead coefficient of 1, it's really easy. It's just natural log of that. And in this section, you'll do so many of these types of problems that you'll automatically do that. Because this section, the integrals in this section are going to be easier than what you've been working on, especially like 7.3. Some of those integrals in 7.3 are pretty intense. There's a lot of trig. This section has more algebra, actually. Okay, so let's take a look and see what it is we're going to be doing in this section. So the method of partial fractions refers to the process of expressing a rational expression. Remember, rational expression is just a polynomial divided by a polynomial as a sum of 2 or more fractions. And it's always possible in theory to replace a complicated rational expression by sums of simpler fractions that can be integrated using previous integration techniques. So it says it's always possible in theory. So some of these rational expressions, really you would need some software for to really simplify them. But we're not going to run into anything like that. So ours are all going to be factorable, just normal techniques. And what happens is the thing that guarantees this is something from abstract algebra or modern algebra called the fundamental theorem of algebra. And this just guarantees that any polynomial can be factored as a product of linear factors. Okay, these are factors of the form ax plus b, and also irreducible quadratic factors. So quadratic factors are of the form ax squared plus bx plus c. And irreducible just means that there's no, it can't be factored basically. Or also what it means is that b squared minus 4ac is less than 0. So if you're going to use a quadratic formula on this particular one, you get a negative under the radical. When that happens, it means there's no real solutions if this were an equation, if set equal to 0. And it also just means that you can't factor it. So some of these trinomials like this can't be factored, so they're said to be irreducible. But basically, it's actually a little surprising. Like any polynomial, no matter how gigantic or how crazy looking it is, any polynomial can be factored into a product of linear factors and quadratic factors. All right, so how do we use this theorem? Well, here's what we do. It actually looks like a lot, but it's really not. It's not a lot. We're going to, when we're going to use this method of partial fractions, we factor the denominator. We use these factors as the denominators in our new fractions, and we assign coefficients to the fractions. Okay, this is all sort of automatic. And then we solve for the coefficients, and there's 3 ways to do this. So I'm going to show you all 3 of them. Okay, the first way, equate coefficients. This is a kind of standard way it's taught. It's slow and methodical. I don't particularly like it because it just takes a long time. So I'll show you one with this so you can see how it's done. The way that I prefer, and most of you will probably prefer also, just to plug in values. So I'll show you that way too. This is the way that I normally do it. And then there's a cover-up method. If you have linear non-repeated factors, this method is really fast. It used to be a secret, I think, because I'd never even heard of it until grad school. But I'll show you this one too. This one is really, really nice if you have linear non-repeated factors. But the one we'll mainly concentrate on is just these plugging in values. All right, so we go back to this problem, and we already know how this is expressed as a sum of partial fractions, because if you remember, we started with a sum of partial fractions and added them together to get this. Well, actually, I guess we subtracted them to get this. But what we do is we start off and we factor the denominator. So if we factor the denominator, we basically have this. We've got minus 2x minus 19. Well, let me start right from the start. X squared minus x minus 6 equals. Okay, so I factor the denominator. Okay, and this factors into a product of x plus 2 and x minus 3. And then we're going to use these factors as the denominators in our new fractions, and we're going to assign coefficients to the fractions. Okay, so all we're going to do is say, all right, I'm going to make one fraction, have a denominator of x plus 2. I'm going to add it to another one with a denominator of x minus 3. And I'm going to assign coefficients in here. I'm just going to call it a and b. And then that theorem from modern algebra says that there will be a way to do this. There's going to be a way to find a and b such that these are actually exactly equal. Okay, so the first way we look at is equate coefficients. Okay, and the name makes sense when you see how it works, but here's what you do. So let me first make a little note here. So this is going to be, first method we look at is we're going to equate coefficients. Okay, so when you do this one, let me start off with what we've got here. X plus 2 times x minus 3. And then this is equal to a over x plus 2 plus b over x minus 3. So the first thing we want to do is eliminate these fractions. So what we want to do is multiply each side of this equation, right, each side of this, by this denominator. So when you actually do this, you won't actually write this out because very predictable things going to happen each time. But let's just say we're going to do this. I'm going to multiply this by this over 1. Then I'm going to have to multiply this by the same thing, x plus 2 times x minus 3. So in this case, when I multiply here, these just completely cancel. But here, this is going to have to distribute through, right? So on the left side, this cancels with this, and we just get minus 2x minus 19 equals. And this will always happen. The first step, you're always going to just be left with this numerator, because whatever this denominator is, you're going to multiply each side by that, so it'll always go away. Now over here, when this comes through here, it's going to distribute through here, and notice that under the a is this x plus 2. This x plus 2 will cancel with this x plus 2, right? Because this is coming through, it's going to distribute here and then here. And it's the whole thing that's coming through. So when it comes through here, the x plus 2 on the bottom knocks out that x plus 2, and the only thing that makes it really is x minus 3. So we get a times x minus 3. The same sort of thing happens over here when this distributes through here. The x minus 3 will knock out that x minus 3, so just the x plus 2 will remain to get multiplied by the b. And so that's why we really don't usually write this in red here. We just automatically go to here. Because you look at the problem you're starting, you're like, okay, there's x plus 2, x minus 3. With the a, the x plus 2 is going to be gone, so I'll just have x minus 3 left. And over here, with this term, the x minus 3 will be gone, and I'll just have x. Oh, look at that. What was I thinking? Okay, let me erase that. Must be getting old. Okay. Were you guys screaming at the computer saying, oh my gosh, Kurt, you're doing it again? Okay, this is supposed to be b times x plus 2. Okay. Because the x minus 3 will knock out that x minus 3, right? When it comes through to multiply, x minus 3 wipes out that x minus 3, and we're just left with x plus 2. So you get b times x plus 2. Okay. With the equating coefficients method, what we're going to do now is we're just going to distribute the a through and distribute the b through. So we'll get this equal to ax minus 3a plus bx plus 2b. Then what we want to do is put all the variables close by. So we've got an ax and a bx. We want to put those next to each other. Ax plus bx. And everything else we'll put together also. And now to equate coefficients, we want to see this x as a negative 2 in front of it. We want to see how many x's do we have here. So I'm going to have to factor out an x. Okay, so I'm going to factor out this x. Maybe I'll do it like this, a plus b. I'll put the x in the back here. Same idea though, right? Because if I distribute this x through, I'd get ax plus bx. But I'm going to put it here for a reason you'll see in a second. And then I'll carry this down, so we have minus 2x minus 19. We still have minus 3a plus 2b. Okay, so here's the reasoning behind why we can equate coefficients. So if this side of the equation is exactly the same, it's equal to this side of the equation. Well, this is a linear expression, so this would have to be 2. And also, since in front of this x is a negative 2, then these are going to have to also be equal to negative 2, right, to make this equal. So we can see that a plus b has to be equal to negative 2, or these won't be equal, right? It says they're equal, so whatever's in front of this x must be the same as in front of this x. Think of it as a slope, right? If these lines are the same line, this is a slope of negative 2, which means this slope must be negative 2. But also, negative 19 has to be the same as these, right? So negative 19 has to be minus 3a plus 2b. So at this point, we have a system of equations. We've got 2 equations and 2 unknowns, right? So I'm going to solve by substitution. I'm just going to solve this for a. So I'm going to subtract b and say a equals minus 2 minus b. I'm going to take this and plug it in right there. So we get negative 19 equals negative 3 minus 2 minus b plus 2b. So negative 19 equals 6 plus 3b plus 2b. Okay, so negative 19 equals 6 plus 5b. I'm going to subtract 6 from each side, so I'll get negative 25 equals 5b. So divide each side by 5, and that implies that b equals negative 5. Okay, so b equals -5. Now once we know b equals -5, we can come back right here, right, or right here. A equals -2 minus b, so b equals -5. That would mean that a equals -2 minus -5, which is plus +5, so a equals 3. Okay, so that means that this is the same as if we put a 3 here and a -5 here. So it'd be like 3 minus 5 over this. All right, so that is equating coefficients. Slow, methodical, works just fine. It's a little too slow. So the next process we're going to look at is just where you plug in values. Okay, so process number 2, technique number 2, we'll say plug in values. You just plug the values in. Okay, so for this one, I'm going to start back where we were, -2x minus 19 over x plus 2 times x minus 3. We start off the same way, x plus 2 plus b over x minus 3. So we start the same way. We even do the first step. The first step is the same, where I'm going to eliminate all the fractions. So I'm going to multiply both sides of the equation by this denominator here. So I multiply this side by the denominator and it wipes it out. I'm just left with -2x minus 19. And over here, let's see if I can do this correctly this time. So multiply this denominator by this, it basically would come through, right? It would distribute through. But what's going to happen is when I multiply this side of the equation by this, when I multiply this term, the x plus 2 will wipe out that x plus 2, and just the x minus 3 will get multiplied by a. So you get a times x minus 3. And over here, it's the exact opposite. There's an x minus 3 here, so that x minus 3 will wipe out that x minus 3. And we'll just have b times x plus 2. Okay, so from here, when you plug in values, we just pick easy values. So looking at this, we want to pick values I can plug in for x that make one of these terms disappear. So like, what if I let x be 3? If I just let x be 3, this wipes this whole term out, and we can solve for b. So I'm going to pick an easy value like that. I'm going to say, okay, let's let x equal 3. So I'm going to plug in 3 in for all of the x's. So I plug in a 3 here. I'm going to get -2 times 3, which is -6 minus 19. So let's see, get -6 minus 19 equals, well, 3 here is just going to make this be 0. And we'll get b times 3 plus 2, which is 5b. This makes -25 equals 5b, which means if you divide by 5, b equals -5. Okay, and then to make another easy one, I'm going to pick a -2, right, to wipe, or sorry, over here. If I pick a -2 here, it will wipe this term out. So then I can find a. So let's let x equal -2. So x equals -2. And then I go right back up here, right, plug -2 in. So -2 times -2 is +4. So I get 4 minus 19 equals, and let me see once. Let me go back here. This is where I'm plugging the numbers in, right? So plugging in -2 here, I'm going to get a times -2 minus 3, which is -5. So I get -5a. And then, of course, when I plug in a -2 here, I get -2 plus 2, which is 0, which wipes out this term. So this gives us -15 equals -5a. Divide by -5, and we get a equals 3. Same as what we got before. This is just easier to get and quicker. And there'll be times when you're doing this and you can't get something to cancel out, which is okay. Just pick a real easy one. Like if you can't get something to cancel out, just pick an easy number like 0 or 1 or something like that, and it'll still, eventually you'll be able to figure out what the coefficients are. All right, and finally we'll look at the third method, the cover-up method. Sometimes this is also called the big thumb technique, or sometimes the Heaviside big thumb technique, named after Oliver Heaviside, who was a electrical engineer who apparently used to use this method. So what we do here is we don't even have to do the first step of multiplying. We don't have to get rid of the fractions with this one. So we can start right at the original problem, and we don't even have to get rid of the fractions. So you have a over x plus 2 plus b over x minus 3. Okay, so with the cover-up method, think of it like this. Okay, I'm going to find what a is. I'm looking for a. And notice down here underneath the a there's an x plus 2. So if I were to let x be negative 2, I'd get a division by 0 here. So basically what you do is I'm going to plug negative 2 in here, but I'm going to get rid of the x plus 2. So it's called cover up because I'm covering up this. So I'll erase it on here, but basically if I were at the whiteboard, I'd cover up this with my hand, which I'll erase it here. So I'm covering up that, and now I'm going to plug in negative 2 for all of these. And you just basically go, okay, a equals, plug a negative 2 in at the top, and I'm going to get negative 2 times negative 2, which is 4, minus 19, which is negative 15. Plug a negative 2 down here, I get minus 2 minus 3, which is minus 5. So you get a equals 3. Okay, so then if I put this back over there, now I want to find b. Okay, so you look at b and you're like, well, underneath here, if I plug in a 3, I get division by 0. So I'm going to plug in a 3, but I'm going to get rid of the x minus 3 over here. So now I cover up this. So this is covered up. So I'll get rid of that. And then you plug in 3 for all of these. Plug in 3 for all of these. So that will give us b equals, if I plug in a 3 here, I'm going to get minus 6 minus 19, which is minus 25. And then on the bottom, 3 plus 2 is 5, so you get negative 5. Okay, so that's the cover-up method. Now this only works when you have linear non-repeating factors, but when you have them, it's pretty fast. But all three of these methods gave us the same thing, and they would allow us to break down that rational expression into a couple easier expressions that we can integrate without any problems. All right, so hopefully that made sense. And now we're going to just look at a general summary for how we go about doing this. So sometimes the denominator just has linear factors, first degree factors like this. So there's no, 2x squared minus 3, just 2x minus 3, just 3 linear factors. When this happens, what we do is we set our little partial fractions up like this. We go, okay, we're going to make these be the denominators. All right, just like we said before, we're going to have each of these will be a denominator. And then we put these coefficients in here, A, B, C. You basically just go right down the alphabet. Okay, so if we've got something like this with linear factors, we just set it up like this, and then we would go about using one of those techniques. Probably what we would do is use the plug-in values technique. That's the way that I usually do it because it's kind of an easy way to go. Okay, so this is kind of an easy case. You just have linear factors. We just set it up like this, and then we would get to work finding A, B, and C. So sometimes you're going to have linear factors raised to powers, like x plus 3 cubed or x squared. You could think of this like a linear factor x minus 0 or x plus 0 squared, right? So when we do that, we have to account for each one of these powers. So like this x plus 3 cubed, we're going to have to consider x plus 3 squared, and x plus 3 cubed. This one we're going to have to consider x and x squared. So when we set it up like a over x plus b over x squared. So we need to account for each power. Then we have plus c, which should just be over x minus 2. And then we're going to have x plus 3 x plus 3 squared, and finally x plus 3 cubed. And we'll just keep on going down the alphabet, A, B, C, D, E, F. Okay, now these ones are kind of long and more complicated than what you're going to see, but I'm just using these to show how this works. And it's abstract algebra that tells us this should work. So it looks weird, like sometimes students say, how do you know that's even going to work? We could always check it. Like when you come up with these, if you really wanted to, you could add all these together and see if you get back here. But this is how we do it. This technique will work. It'll, going through one of those 3 methods, will find all these coefficients for us. Okay, so these are all linear factors, but now we're going to have some irreducible quadratic factors. So irreducible quadratic just means that, well, you could see like b squared minus 4ac is less than 0. So if you're going to use the quadratic formula, you would find out that there's a negative under the radical. So if you have something, it also just means it can't be factored. So if you have x squared minus 1, we can factor that, right? That's difference of perfect squares, x minus 1 times x plus 1. But if we have x squared plus 1, that one can't be factored, not over the real numbers, right? You can't factor that one. So this one is irreducible. Okay, so that's what that, when you see that word, that's what they're talking about. Okay, so in that case, when we have those factors, let's see what we do here. Okay, so with this one, we are going to write this as this. So the first term, the x minus 2 term, we already know what to do there. That's just a over x minus 2. Now, when you have the second degree, the irreducible, it's going to look a little different. So I'm going to put that down there, x squared plus 1. And then what we do is we have a linear term on top, bx plus c. And I'm just going down the alphabet, right? A, B, C. But when this is a second degree, we're going to have a linear term up here. So this one will also have one. So then we're going to go plus, we'll have 2x squared plus x plus 9 over dx plus e. Okay, so that's how you work with the irreducible quadratic factors. And then the other thing that could happen is if the numerator power is greater than or equal to. I'm going to emphasize the or equal to. That works too, but greater than or equal to. When that happens, we have to do long division. Everyone's favorite, long division. So, I wonder how many of you have not done long division in more than a year. Probably quite a few. So, we may need to practice this one. So, let's see. We look at this problem, and the numerator power is definitely greater than the denominator power. So, when that happens, we're going to have to do this long division. And it works just like regular long division, like 20 divided by 8. It works just like that. So we're going to take this x cubed and divide it by this. So let's see what we'll do. We'll have x squared plus 2x plus 1. And then what we do, we put the x cubed here, and we put a little placeholder for everything else. 0x squared plus 0x plus 0, just to keep track of things. And what we do is we think of, what could I multiply this by to turn it into that? And it's going to be x, right? If I multiply x by x squared, I get x cubed. So then you take this x and multiply this whole thing. So x times x squared is x cubed, x times 2x is plus 2x squared, x times 1 is plus x. Then what we do, just like we do a normal long division, we're going to subtract. So I subtract. So basically I need to take a negative and distribute it through all this. So all these signs change, right? So I get a minus here. This becomes a minus. This becomes a minus. And then you just combine these columns. So x cubed minus x cubed is 0, so that goes away. 0x squared minus 2x squared is going to be minus 2x squared. And 0x squared minus x is going to be minus x. Okay, so then we think about, okay, now I'm above this other column. What could I multiply this by to turn it into this? Well, I could multiply this by a negative 2 to get that. So we go minus 2. And then what I do is multiply this whole thing by negative 2 one at a time. So that would give us negative 2x squared minus 4x minus 4. And then what we do, just like with regular long division, again, we subtract. So basically all the signs are going to change. So I'm going to get plus, plus, plus. And then just like these canceled before, this will cancel. And we will get plus 3x plus 4. Oh my gosh, I did it again. I did it again. Look at this. This is supposed to be a 2 there, right? That's a 2. Because when I go negative 2 times this, over here I get a minus 2. Oh my gosh. All right, let's fix this thing here. That's got to be a 2. Getting old. Don't get old. It's no good. Nothing good about it. Okay, so then basically what this is our remainder. I'm not sure why I really put the plus there, but 3x plus 2 is our remainder. So just like what you could do before when you were doing long division, we could go plus and then just put 3x plus 2 over the original, over this original x squared plus 2x plus 1. But what we'll end up doing anyway when we end up doing this is we'll end up factoring that. So I'm going to factor it as x plus 1 times x plus 1. Okay, so hopefully that made sense. We have to do this long division, and then, so if we were going to integrate this, then we go ahead and integrate this, right? And these two, of course, should integrate easily. And this, we're going to have to use partial fractions to expand this, so we can integrate that part. But that is just some of the fun that is awaiting you in these homework problems. But we've got to get ready for them, so we'll look at a couple of them in these notes and then let you loose on the homework. All right, so let's take a look at this example. We've got an integral here. And you notice the denominator. This, we have to see if we can factor this, which this is factorable. So what we could do, you can just notice x squared plus 2x plus 1. That does factor into x plus 1 squared. All right, so really what we've got here is, I guess I'll do it right here. We'll say x squared over x minus 1 times x plus 1 squared, right? Because this is just x plus 1 squared. Okay, so we're going to set this up so it'll be a over x minus 1 plus, remember, since this is squared, we need 2 of these. So we have b over x plus 1, and then another one, c over x plus 1 squared. So then the first thing we need to do here is just multiply both sides of the equation by the denominator. And when we do that, as I mentioned before, every single time what's going to be left on the left is just the numerator. On the right, if you look at this, when I multiply this term by this whole denominator, the x minus 1 will take that out, but there'll still be x plus 1 squared. So we're going to end up with a times x plus 1 squared. Right, because without me really writing it, it's sort of like taking this denominator over here and distributing it through here once, twice, 3 times, right? So when this denominator comes through and hits this term, the x plus 1 will knock out one of these, but there'll still be one left. So the b will be multiplied by x minus 1 and one of those x plus 1s. right? And then this term, when we multiply by this term, the x plus 1 squared, will take that out, but we'll still have x minus 1. So this will be plus c times x minus 1. Then at this point, this is where we can just start plugging in some numbers, right? So we could pick, there's an easy one like 1, right? I can just let x be 1, and I can see a bunch of, well, a couple of these terms will completely go away. So I'm going to purposely pick ones like that. I'm going to pick x equals 1. I'm just going to plug 1 in for all the x's. So x squared is 1 squared, so I get 1 equals. Now this, when I plug in a 1 in here, I'm going to get 1 plus 1, which is 2, squared, which is 4. So I'm going to get 4a. But the 1 here will make this 0, so that will be gone. The 1 here will make that 0, so that will be gone. So basically 1 equals 4a, and that implies that a equals 1/4. Right, if I just divide each side by 4, I get a equals 1/4. Okay, so now I'm going to try a negative 1, because negative 1 will take out some of these. So I'm just going to let x equal negative 1. So I'm going to plug negative 1 in here and square it. Negative 1 squared is still going to just be 1 equals. Negative 1 will take this out. This negative 1 will take that out. And all we'll be left with is c times minus 1, which is c times negative 2, which is negative 2c. So if we divide each side by negative 2, we'll get that c equals negative 1/2. Okay, so we got A, we've got C, now we just need to find B. So to find B, there's nothing else that will make these go away, so just pick an easy thing like maybe 0. All right, I'm just going to let x be 0. That'll be pretty easy. So plug a 0 in for x squared. I plug a 0 in here and square it, so I'll get 0 equals. Plug a 0 in here, I'm just going to get 1a, so I'll just get a. And then, let's see, we'll get a 0 here, so I'm going to get a negative 1 times 1, so I'll get minus b. Then plug a 0 in here, and we're going to get negative 1 times c, so I'll get minus c. So 0 equals a minus b minus c, but we know something about a and c, right? So that means I can say, all right, so 0 equals 1/4 minus b, and then plus c, or minus c, which would be plus 1/2, because it's minus c and c is negative 1/2. So we were going to get 0 equals 1/4 plus 1/2 is 3/4, so get 3/4 plus b, 3/4 minus b. So then I just add b to each side, and I'll get b equals 3/4. Okay, so now we know what the coefficients are. All right, so now we can write our integral. Just have to rewrite the integral. So what we'll have now is our integral, which was x squared over x minus 1. I'm just going to rewrite the original one. X squared plus 2x plus 1 dx. All right, well, that is going to be equal to, we'll say 1/4, that was a over x minus 1 dx, plus b was 3/4 over x plus 1 dx, and then minus 1/2 over x plus 1 squared dx. And then what I'm going to do is pull out these coefficients in front. Okay, so like the 1/4 I'll pull out here, 3/4, 1/2 I'll pull out there. So then we'll get, this is equal to 1/4, 1 over x minus 1 dx, plus 3/4, 1 over x plus 1 dx, minus 1/2, 1 over x plus 1 squared dx. And then these first two, these are going to be pretty simple. They're just natural logs, right? So those are like the ones we looked at before. If you do a u substitution, you let u equal x minus 1. You're just going to get 1 over u du. So this is going to be a natural log. So this is going to be 1/4 natural log absolute value of x minus 1. Same thing with the next one, 3/4 natural log absolute value of x plus 1. Okay, now this one's going to be different because this is not just x plus 1. This is x plus 1 squared. Okay, so I'm going to just ignore the negative 1/2 for now and just kind of take this one off to the side here. And let's say we're going to do this problem, 1 over x plus 1 squared dx. And we could do a u substitution here, right? We could say let's let u equal x plus 1. Du would be dx. So we'll get 1 over u squared du. And that's equal to u to the negative 2 du. And now we can just use the power rule, right? So that is going to be u to the negative 1 divided by negative 1 plus c, which is a very strange looking and awkward looking expression, but I can bring this down here if I make it a positive one, right? So really that is just, what's probably a better way to say that would be negative 1 over u plus c, right? This is the same as this. They're both negative. Dividing by 1 doesn't do anything. I just move the negative out front, and u to the negative 1 is 1 over u. Okay, so then I can take this. So since u is x plus 1, I would get this plus c. So now using that, I'm going to put it back over here. So we're going to have the negative 1/2. So you have minus 1/2, and then the answer we just got was negative 1 over x plus 1 plus c. So then we can just clean this up a little bit. You can say this is equal to 1/4 natural log absolute value of x minus 1 plus 3/4 natural log absolute value of x plus 1. Then this would be plus, right? You multiply negative times negative, so you get plus 1/2, and you can write this however you want. 1 over x plus 1. I guess you could write it like that if you want, plus c. Or, of course, you could distribute the 2 through here if you wanted to. All right, but that should be the answer to example 4. So hopefully that one made sense. And let's take a look at example 5. Have you take a look at one more, and then I think everyone should be ready to go on the homework. And, of course, it just takes practice, right? It's not good enough just to watch me do these. The only way to really learn them, as you know, you have to do the homework. So make sure you try the homework and let me know if you run into any trouble. So looking at this one, we've got a irreducible quadratic on the bottom. So I'm just going to maybe off to the side here. Let's set this up. So you get 1 over x plus 1 times x squared plus 1. So we know that's going to be a over x plus 1, and then plus bx plus c over x squared plus 1. Because remember, when we've got the quadratic, we need a linear expression up here. Okay, so then what I'm going to do, same as always, going to multiply both sides by the denominator. So if we do that, we're going to get 1 equals a times x squared plus 1 plus bx plus c times x plus 1. And then from here, we can just start plugging in some numbers. So the only real obvious one right now is negative 1. So I'm just going to let x be negative 1 and see what happens. So we get 1 equals negative 1 squared is 1 plus 1 is 2. So we get 2a. And then over here, the negative 1 is going to make this 0, so it wipes this out. So we get 1 equals 2a. So we know now that a is equal to 1/2. Right, divide both sides of that last equation by 2, and we get a equals 1/2. Okay, so now there's really nothing else that will cancel, but it's okay. We can just pick easy numbers. So I'm just going to plug in a 0 for x, because it's kind of an easy one. So I'm going to say let's let x equal 0. So I'll get 1 equals, that would be a, right? Because I plug a 0 in there, so I'll get a. Now over here, that when I plug a 0 in here, that's going to be gone, so I'll just get c times 1. So I'll get 1 equals a plus c. Okay, so a is 1/2, right? So this means 1 equals 1/2 plus c. So if I subtract 1/2 from each side, I will get c also equals 1/2. Okay, so I've got a and c. We just have to find b. So I'm just going to pick another kind of easy number. So I'm just going to pick one. I'll pick 1. I'm going to let x equal 1. You really can pick anything you want. If you really wanted to pick 11/3, you could. I wouldn't recommend it though. I'd pick an easy one just to make the arithmetic easier. So I'm going to let x equal 1. So I'm going to get 1 equals. If I plug a 1 here, I'm going to get 1 squared plus 1, which is 2a. So I'll get 2a. And then I plug in a 1, I'm going to get b plus c times 2, right? Because this will be 2, this will be b plus c. So I'm going to distribute this 2 through, and I get 1 equals 2a plus 2b plus 2c. And now we just make use of the fact that we know that a and c are both 1/2. So if I put a 1/2 in here, I'm going to get 2 times 1/2, which is 1. Same thing over here. I plug in a 1/2 for c, I get 2 times 1/2, which is 1. So that'll give us 1 equals 1 plus 2b plus 1. So we've got 1 equals 2b plus 2. So I'm going to subtract 2 from each side. Subtract 2 from each side, and we will get minus 1 equals 2b. So then if I divide each side by 2, you get b equals negative 1/2. So now we've got all 3 of them. So now we are ready to go. So let's make a little room here. I've got my a, b, and c. So I'm going to rewrite the original question, and we'll go like this. So the integral dx over x plus 1, x squared plus 1. This is equal to 1/2 over x plus 1 dx plus, so for the bx plus c, we're going to get negative 1/2 x plus 1/2 over x squared plus 1 dx. And now I'm going to do what we have been doing and pull these coefficients out front, including this. You got to figure this one out. So pull this out front, so we'll get 1/2 1 over x plus 1 dx. So that one's pretty easy. Now this next one, I'm going to pull out a negative 1/2. And if I do that, in the numerator, I should get x minus 1. Right? Because if I distribute this through, negative 1/2 times x is negative 1/2 x. Negative 1/2 times negative 1 is positive 1/2. Okay? So looking at these integrals, we know this one, right? This is just a natural log. This one's a little trickier, though. So there's no u substitution that works. This one, we're going to have to actually split this into 2 parts. Okay, so what we can do with this one is this. We can say, okay, I'm going to just copy this one down here. But this one, if I pull out the 1/2, I could do this. If I pull out the 1/2, I could say this is equal to x over x squared plus 1 dx minus 1 over x squared plus 1 dx. Right, because all we really did is I took this and I said, okay, that's equal to x over x squared plus 1 minus 1 over x squared plus 1. Right, if you split it up like this, Because think if we were going to add these, we've got common denominators, we could just go, oh, it's x minus 1 over that common denominator, right? So if you split them up like this, then they can each have their own integral. And now, at this point, this integral, you could do this one right after section 5.5 in the Stewart book, because this one is U substitution. This one you've seen before. This is on, if you have any like common sheet of integrals in any calculus class, this will be on. There's just one we don't see a lot. Although if we didn't know anything, we could find this one by trig substitution, the technique from 7.3, although I wouldn't recommend it because this is one that we've seen before. Okay, so let me just, while you're thinking about that one, I'm going to distribute this negative 1/2 through. Okay, so let's give us 1/2, 1 over x plus 1 dx, minus 1/2, x over x squared plus 1 dx. And then this would be plus 1/2, 1 over x squared plus 1 dx. All right, so if you recognize this one, raise your hand. Okay, some of you recognize it, some of you don't, some of you are not raising your hand. Well, this one is actually the antiderivative of this is inverse tangent or arctangent. It's just one we don't see very often, but it's out there. So this one has a solution. We know the solution to this one, and we can find this one. Okay, so I'm going to do this one off to the side here. I'm going to ignore the negative 1/2 and just think if it were x over x squared plus 1 dx. Okay, this is a perfect one for u substitution. We can say u equals x squared plus 1. du equals 2x dx. Multiply each side by 1/2, and you get 1/2 du equals x dx, which is good because x dx is exactly what we've got up here, right? X dx. So then we can substitute this in, and we get 1/2. We'll get 1 over u du. So this ends up being also a natural log. So you get 1/2 times the natural log of u plus c, or in our case 1/2 natural log of x squared plus 1. Now in this case, because x squared plus 1 cannot be negative, you could just put parentheses here. You can use absolute value if you want to, it doesn't matter. Okay, but then from here, now we should be able to answer, we should be able to finish the problem. Let me make a little more room here. Okay, so we'll kind of go around here. So our answer is 1/2 natural log of x plus 1, right? Because we knew this one because we've seen them like this before. Lead coefficient is 1 here. So if we do a u substitution, this is going to be 1 over u, right? So it's going to be the natural log of the absolute value. And let me make sure that absolute value looks like an absolute value. That's got to be a line. Okay. So absolute value. And then over here we've got minus 1/2 and then times this, right? Actually this part. Minus 1/2 times 1/2 natural log. This one doesn't have to be absolute value. And then we've got plus 1/2. Okay, so this one right here, the answer to that is the inverse tangent or the arctangent of x, and then plus c. So then to clean it up, we would get x plus 1 minus 1/4 natural log x squared plus 1. And again, you can leave absolute values on here if you want to. It's fine. Typically in the back of the book or in the back of any textbook, any calculus resource, when this can't be a negative, then for natural log, they'll probably typically just put it in parentheses, but it doesn't really matter. And plus 1/2 inverse tangent of x plus c. So As you can see, once we get these set up, the integrals are typically a little easier than what we've been dealing with. But you have to get the technique down, so make sure you try them out, get some practice with how to break these things apart. And as always, it takes a lot of practice. Also, as always, if you have any questions, just let me know. So best wishes with this section, and I will talk to you soon.